Welcome back, everyone. This video continues our series on the philosophy of mind by talking about the Turing test. We're going to start out by distinguishing two puzzling aspects of the mind, which will lead us to a question about machine intelligence. And in trying to answer that question, we'll introduce the Turing test. We'll talk about what the test is, what its advantages are, and how you might appeal to this test to argue in favor of the possibility of computer intelligence. So, we've seen a number of reasons that many philosophers find convincing for believing that the human mind could eventually be fully explained by the physical sciences. But there's two aspects of the human mind that seem to be roadblocks to achieving this goal, to explaining the mind in purely physical terms. The first is the fact that human minds have phenomenal consciousness. This is the subjective character that accompanies our experiences. It's how an experience feels from the inside. Sometimes this is described as the fact that for conscious creatures, there's something it feels like to be you or me. Sensations provide a prime example of phenomenal consciousness. There's something it feels like to feel a pain. There's something it's like to have a visual sensation of a rainbow. And there's something it's like to hear music, to hear the music of Madame Gandhi. And each of these experiences feel different to the person who has them. They are unique. What it feels like to me to have a pain is different than what it feels like to me to listen to the music of Madame Gandhi. Now, presumably, certain things in this world don't have phenomenal consciousness. I don't think that there's anything it feels like to be a rock. I don't think rocks have subjective experiences. But there are creatures other than humans that I think do have this kind of consciousness. Presumably, there's something it's like to be a bat, even though I assume that it feels very different to be a bat than it does to be a human being. The other aspect of the mind that's difficult to understand is intentionality. This refers to the way that our mental states can be directed at or represent some other thing. Intentionality is most closely related to the idea of thought, thinking, or intelligence. So beliefs, desires, and hopes are paradigm examples of mental states that represent things. So my belief that Minneapolis is in Minnesota represents the city Minneapolis, the state Minnesota, and the relationship between those two. My belief that 2 + 5 = 7 represents the number 2, the number 5, the number 7, the operation of addition, the relationship of equality. Now, my beliefs exist in my mind, but what they represent is independent of my mind. So the city Minneapolis, even though my belief is about Minneapolis, the belief's in my head, but the city that my belief represents is outside my mind. So the human mind can form representations, such as our beliefs and desires, about the world around us. But many physical objects, such as a rock, or a physical process such as photosynthesis, they don't have the ability to think. They don't have any thought processes going on. They don't represent anything. So we can illustrate the ways in which these two features are puzzling by considering the fact that technology like an EEG machine, fMRI, depth electrode, can scan our brains and record complex patterns of neurons firing in our brains when we experience things like pain or when we have the thought about a loved one. However, it isn't clear why a specific pattern of neurons firing would be associated with a specific feeling that we call pain, or why it'd give rise to any subjective feeling or experience at all. So seeing those neurons firing, learning that those neurons are firing, doesn't tell us what it feels like to be in pain. Similarly, why should we think that a specific pattern of neuron is firing is associated with the thought about my daughter or about the number 2? So this raises a question. How should a physicalist attempt to discover an explanation for how a purely physical process could give rise to these two features of our mind? Now, one way to try to understand how something works is to look inside, see it working, and break it apart and see how those parts work together. For instance, if you want to know how a cow heart works, you might dissect it in a biology lab. This is the approach that neuroscience takes to the mind. It attempts to look in the brain, see what neurons are firing, and see how all those parts work together when we're experiencing things or thinking things. But another approach is to see if you could build one yourself. So one way to see if you understand flight is to see if you can build an airplane. This is the approach that artificial intelligence takes. It tries to build a machine, a computer, with a thought process in order to better understand that thought process. Now note, there isn't always a clear divide between these two approaches. You might use a little bit of both. So this raises the question, could we build a machine that has a mind, intelligence, and the same ability to think about and understand all the subjects and topics that the human mind is able to? This is the question that Turing is trying to consider. But he thinks that the question is ambiguous in a few ways. Firstly, are there any limitations on what kind of machine or engineering process that we could use to try to build this machine with a thought process? Well, probably, because in some sense, a clone is a machine built by the work of scientists. But the fact that scientists could create something with a mind and intelligence by cloning a human being wouldn't really teach us anything, because we already know that the machinery of a human being, a brain and nervous system, is capable of intelligence, thought, and understanding. So we wouldn't learn anything new by being able to do that. So Turing makes the question more specific by asking about a specific, well-defined kind of machine known as a digital computer. So what you're probably thinking of when I talk about computers. So Turing wants to know if a machine built out of these kind of materials that uses this kind of process would be capable of having thoughts. So Turing goes into detail describing what a digital computer is, but for our purposes, we only need to note that a digital computer will consist of 3 parts on his explanation. There's the store, the executive unit, and the control. The store is the part of the computer that stores information. Think of this like the memory. Now, one important part of the store is analogous to a book of rules for the computer to follow. Building this rule book is what you would call the act of programming a computer. The executive unit is then the part of the machine that carries out or performs the individual operations in a calculation. And then the control is the part of the machine that is in charge of making sure that the rules in that rulebook or the instructions are followed correctly and that they're followed in the right order. But this question, can digital computers think, is still ambiguous in another sense, because once we build and program a computer, we still need to figure out, well, does it literally have thoughts, intelligence, and understanding? Notice the question is whether or not it literally has thoughts, not whether it metaphorically does. Similarly, I might say that my garage door opener metaphorically knows that I'm underneath it because I trip a sensor and it stops from going down further so it doesn't crush me. But I don't think my garage door opener literally knows anything. But another problem is that we can only ever observe the thoughts in our own minds. I can experience my pain, I can be aware of my own thoughts, but I don't experience your thoughts. So even if we created a computer that had thought, we wouldn't be able to experience and observe its thoughts directly. And so we need some way to decide once we've built it if it has thoughts or not. And the problem is that it isn't clear what methods we should use to detect the presence or absence of thinking in the computer once we've built it. So Turing proposes a solution to this problem by developing what he calls the imitation game. Today we simply refer to it as the Turing test. So here's the test. There's 3 subjects, a human interrogator, a human interviewee, and a computer interviewee. They are all placed in separate rooms where they can't see one another. They're allowed to communicate, but only via text-based messages. And the interrogator gets to ask either subject any questions that they want about any topic whatsoever. And then the interviewees are to send replies in text form. The interrogator is then attempting to use the replies to figure out which room has the human interviewee and which room has the computer interviewee. The human interviewee wants to reply in a way that would help the interrogator. So they don't want to confuse them. They don't want to trick them. The humans are on the team together, you can think. The computer is programmed in a way to try to trick the interrogator. So the computer's goal is to get the interrogator to believe that it is the human. Now, if the interrogator cannot distinguish the human replies from the computer replies, then the computer is said to have passed the Turing test in that case. Turing's claim is that if we were to build a computer that passed the Turing test, that would be a good reason to believe that the computer has intelligence or a mind or literally has thought processes going on. So what are some advantages of this test? Well, firstly, it's a concrete test with clearly defined parameters. We know how to go about doing this. And anything that is ambiguous, we can still define. So how long does the interrogator get to ask questions? Well, we can set a specific time limit, maybe 5 minutes, 10 minutes, whatever you want. It also appeals to observable results that can be recorded. So even though I can't experience a computer's thoughts, I can experience and observe the responses that they give and whether they are able to trick a human interrogator. Now, the question and answer format of this test also has the advantage of separating intellectual from many physical abilities. For instance, there's physical abilities that humans have. We're able to run, walk, we can throw footballs, we can play basketball, we can paint paintings. But how good you are at painting a painting, how good you are at playing football is irrelevant to whether you have thought or whether you have a mind. But whether you're able to answer questions about those topics seems to be relevant to whether you have intelligence capable of understanding those topics. The question and answer format of the test also has the advantage of being completely general. We can adapt it to any topic that humans are capable of thinking about or understanding. The interrogator could ask questions about math, about politics, pop culture, about history, about relationships, about emotions. Any topic that the human mind is capable of understanding, this question and answer method can test for that kind of intelligence. Moreover, there's a clear analogy between a computer that passes the Turing test and a human mind. If a computer passes, then its replies were similar to the replies that humans give to the same questions. And we believe that it's our thinking and intelligence that allows us to understand the questions and decide to give the answers we do. If the computer is giving similar answers to the very same kinds of questions, shouldn't we analogously explain the computer's replies as being the result of the computer having intelligence, understanding, or thought? The question does arise, would we ever be able to build a computer that passes the test? Now, Turing makes a prediction. He believes that in about 50 years' time, he was writing in 1950, so he's making a prediction about the year 2000, he thinks it will be possible to program computers with a storage capacity of about 109. Now, his unit of measurement that he's using here is quite small, and so he drastically underestimated what the storage capacity of computers will be. But then he also predicts it'll be possible to make computers play the imitation so well that an average interrogator will not have more than a 70% chance of making the right identification after 5 minutes of questioning. Now, at the year 2000, at the millennium, nobody had built a computer that could pass the Turing test. Even today, no computer has passed the Turing test. Some people have claimed as much, but they're playing fast and loose a bit. Turing goes on and says, the original question, can machines think, I believe too meaningless to deserve discussion, because he thinks it's ambiguous. Nevertheless, I believe at the end of the century, the use of words in general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. So he thinks that our language will have changed such that it won't be unusual to talk about thinking machines. And I do think we talk about it this way. We talk about smartphones. We talk about Siri understanding us or not understanding us. But we need to be careful. Are we using this language literally or metaphorically? Such as in the case of my garage door opener knowing that I'm underneath the garage. But this leads us to Turing's argument for computer intelligence. His first premise is that if a machine could pass the Turing test, then it would have intelligence. It would be capable of thinking. So this premise just basically says he thinks that his test is a good test of intelligence. Secondly, he says he believes he's making a prediction that eventually we'll be able to program a digital computer that could pass the test. Maybe not in the 1950s, maybe not even now in 2021, but he thinks that as we improve the capabilities of computers with more storage, more speed, and we tinker around to find the right programming, he thinks in theory we could program a computer that would be able to pass this test. Thus, he comes to the conclusion that even if none of the computers we have right now are genuinely thinking, a digital computer could theoretically be built to have genuine thought processes. So why is this question important? Well, one, if computers can think, then we can improve our understanding of the mind by trying to build one. We could study human minds by building computers with minds whose thought processes mirror that of a human being. So human beings are able to think about arithmetic. How are we able to do that? Well, let's build a machine that is capable of giving the same kind of answers to mathematical questions as a human being. Now, I don't want one that gives all the correct answers because a human being doesn't always give the right answers. What I want to build is a computer that uses a program that answers the same questions correctly that a human being would, but also answers the same questions incorrectly that most human beings would. And once we see that it gives the same correct and incorrect answers, the idea is whatever program it's running, that's the program that explains how the human mind is able to think about arithmetic. Now, second, if a computer could have a mind, then that teaches us that the mind is not identical to the brain, because computers do not have biological brains. They are built out of silicon. And so if a computer is able to have a mind, then the mind must be something other than the brain. Thirdly, if it is possible to create a computer with a mind, then that may raise ethical considerations regarding how we can appropriately interact or behave to that machine. Lastly, if it's possible to create a computer with a mind, then the supposedly science fiction question of whether it would be possible to transfer a human's mind or thoughts onto a computer becomes a genuine question for us to consider. All right, so that's it for this video. In the next video, we're going to see how Turing's views served as inspiration and foundation for the field of artificial intelligence and for what's known as the functionalist view of the mind. I'll see you then. Bye-bye.